Okay, what I'm going to work on in this video is we're going to look at this titration problem I have up here. But for this video, I'm just going to look at the near equivalence point question, which is the 20.10 milliliters added. I'll have a separate video that I'll do all the others in. So for near equivalence is where we have some issues because we have more than one acid present, so we can't just treat it like a single weak acid or a single weak base like with monoprotic cases. You also can't use Henderson Hasslebalch, though, because our approximations aren't good anymore. So that Henderson Hasslebalch assumes that the concentration of both acid species and the base species present are going to stay relatively constant. In this case, that's not true, though. We're right past the first equivalence point, which means that H2 or HA minus is the predominant species, but there's a little bit of A2 minus. But that little bit of A2 minus is unlikely to remain constant because we're so close to equivalence. So we can't use the Henderson Hasslebalch equation. So let's look at how we would solve this. I'm going to start by creating real quick two Ka statements because we'll need those. So I'm just going to call this H2A for the compound that is ophthalic acid for the orthogonal species or the ortho species. So we have H2A plus water is in equilibrium with HA minus plus H3O plus. And then the second equilibrium we have to worry about is HA minus plus water is in equilibrium with A2 minus plus H3O plus. Ka1 for this top equation is, let me see, I got that written down, is 1.12 times 10 to the negative 3. That's supposed to be a 3. There's no reason to write a little squiggly on it. Sorry about that. And then Ka2 is 3. I really can write a 3. 3.91 times 10 to the negative 6. So here are our two Ka statements. Also, I have already calculated, which I will show in another problem, where my number of moles of acid initially, because I'm going to use that a lot in this problem. So if you go and you look at the fact that you have 10 milliliters, oh God, what did it do? 1 second. My screen went away on my side. I can't see this. There we go. I can see it again. So we have 10 milliliters. I really don't like my new marker. Sorry, I just switched to a different pad to do these writings. I'm having to adjust to it. I'm really, I already feel like crap. I really wish this thing would stop. Okay. I can't click on anything that apparently that close to the top. So we're just going to have to go with, I was trying to underline 10 milliliters of 0.2 molar. So when you do that, if you calculate the moles, you'll get that you have 0.002000 moles of H2A to start your problem with. So that's how many moles of acid we have to start. And what that means is when you, in the first and the equivalence point, if you go through and do the calculations for equivalence point, you'll find the equivalence point occurs at 20 milliliters of base added. That's how much base you need to get 0.002 moles of sodium hydroxide to react completely with one of the hydrogens. So that means when it got to 20 milliliters for this problem, all of the H2A would turn into HA minus. So if you're for the 20 milliliter part, you just have a compound that is both an acid and a base in terms of which equation it's going to play a part in. So then you can use an equation we learned from class to deal with that. So we have at 20 milliliters 0.00200 moles of HA minus now because we removed a proton. And now we've gone 0.1 milliliters further. So in that 0.1 milliliters further, we've started removing the second proton because once everything is HA minus, because that was the easiest proton to remove, you'll start removing the second one. And that means we're going to have a fairly large concentration for our value of HA minus and a very small concentration for our A2 minus. So we need to know both of those to be able to figure this problem out. So let me see, where did I do that? That's right at the calculation. Okay, so let's just calculate those two concentrations first. And so these are analytical concentrations. They're how much we have before we start worrying about equilibrium effects. So our concentration of HA minus is we had 0.002000 moles of HA minus, because that's what we had at the first equivalence point, and then we got rid of a little bit more. So that little bit more was the last tenth of a milliliter, so that's 0.00010 liters times its molarity, 0.100 moles per liter. And then for this one, we're going to need the concentration. I'm going to divide by the volume, which is going to be 0.03010 liters. That's 10 milliliters for the sample, 20 milliliters that we've added. When I find this concentration, it's going to be 0.06611 molar. For these problems, I'm going to keep a few extra digits compared to what I might know. So this one, technically, in terms of my significant figures, I only know the to 2 significant figures because of my limitation on my 0.00010 liters. Having said that, I'm going to keep extra digits here so I don't have a rounding error. I'll deal with the number of significant figures I have at the end of the problem. So for here, we need to keep extra digits because we're going to be calculating 2 quantities that are very, very close to each other. And if we round too early, we're going to subtract them and just get 0. And that doesn't make any sense for this problem because we care about the really small amount of difference between them. So that's why I'm going to round the way I am for this problem. Then for my concentration of A2-, A2- is just related to how much sodium hydroxide I added past the equivalence point. Most of these setup problems are thinking through what quantities are turning into what. So you had everything as HA-, and then you make a tiny bit of A2- with the any base you add past the equivalence point. So that's why I'm using the 1/10 of a milliliter. And so that will be from same setup as here, 0.00010 liters times 0.100 moles per liter. And this is still divided by the same volume because it's in the same container. So it's the same total volume. And when you do that, I got 3.322 times 10 to the negative 4th molar. And so this is our concentration of HA- and A2-. Now, I'm going to use both of these, but I'm going to go to another slide so I have more room. But so if you want to make sure you've got these written down somewhere so you can look at these numbers, we'll be using them on the next page. So here, what I need to do now is since I don't have Henderson Hasslebalch and I have at least 2 species, I'm going to need to look at a mass and a charge balance to be able to figure out this problem. So we'll start with the mass balance. In this problem, I'm going to follow the ion, so the oxalic acid, the part that is the A2-, that part only comes from the original H2A, right? So we know how many moles of that we have. We have exactly 0.002000 moles of that substance. At this point in the titration, we have 2 substances that contain that before we start running out equilibrium effects. We had a bunch of HA- and a little bit of A2-. So those 2 concentrations added together, so the HA- plus the concentration of A2- equals all of the A2- species. Now, when we're looking at the equilibriums, some of that HA- is going to turn into H2A. And some of that HA- might turn into A2-, or some of the A2- might turn into HA-. Either way, those can change. So for that reason, we need to account for all 3 species that could become at equilibrium. That's why I'm switching to the brackets here. So I've had a long day. Okay. So H2A plus HA- plus A2-. Those 3 species at equilibrium have to add up to those 2 concentrations. Then we also need a charge balance. So our charge balance, first I'm going to do our positive species. So we have some sodiums, Na+, and we have some H3O pluses. Those are the only 2 positive ions that we have. Note that Na+ at equilibrium we're going to treat it as exactly the same as how much Na+ we dissolve from the sodium hydroxide. So if you wrote like a concentration of Na+ symbol, that'd be fine too. Either is going to give you the same answer in this context. We're not going to suggest the Na+ turns into anything. We're not going to worry about any complexes it might form with other stuff. And also those things, if they're still positive, the charge, we'll still keep track of the charge stuff. So just however much sodium hydroxide we added, each of those makes 1 sodium ion. We'll figure out the concentration of that. Now on the negative side, we have hydroxide ions because since we have an acid, we also have bases, but we'll talk about why that term isn't all that important. We then have HA- because that's a negative species, and then we have 2 times A2-, since each A2- represents 2 negative species. So to balance it out, we would need 2 of the plus ones to balance a -2. Now to make this work, I'm going to need to make an approximation. So the approximation I'm going to make is I am working with, right after the first equivalence point of a diprotic acid. I am going to make an assumption that is fairly good, and we'll see at the end of the problem, that it is an acidic setup, and so H3O plus will be much greater than OH-. That means that this quantity, I can just treat it like it goes away. So it's not 0, but it's so small that if I were to subtract it from the other side and I had H3O plus minus OH-, the minus OH- wouldn't have an effect. So we're just going to treat it like it's not there. So close to 0 because of that, so we're going to treat it as about 0. Remember, you can only do this with addition and subtraction. You can't do this when it shows up in a multiplication or division problem because multiplying or dividing by a small number changes that number. With addition and subtraction, you can. So it goes away. Now, the other things I can note is Na plus is a value I can find. I'm going to calculate that in a minute, but not quite yet. I've got to choose an order to do things in. The way to solve this problem the easiest is I want to get rid of one of the species in my mass balance, so I want to plug my charge balance into my mass balance. The way I'm going to choose to do it is I'm going to solve for HA minus. That'll be my easiest case. Will be the species that's in the middle. The reason I'm doing that is then I'm going to put it into my mass balance, and then I'm going to find all the species in terms of HA minus, and that will be helpful because what that's going to do is HA minus is going to be effectively a constant because it is a very high value. So while A2 minus might change some, HA minus probably won't, and that's a reasonable approximation for this problem. So when I rearrange all this, what I'm going to get is that HA minus is equal to sodium plus H3O plus minus 2 times my A2 minus species. So all of this now is going to get plugged in to my mass balance equation. And so let's write that out. So what I have is that the concentration of HA minus plus the concentration of A2 minus, remember these are both constants, we'll put some numbers in for a second, is equal to H2A plus, now it's all the species we have, so Na plus H3O plus minus 2 times A2 minus. That's all plugged in now. And then we add the last number on, which was A2 minus in the mass balance. So now I've got a number of things to do. I need to simplify this equation down. I want to get it in terms of one variable, which is H3O plus, and I'm going to do this by, I am going to put it in terms of H3O plus and HA minus, and then I'm going to set a value for HA minus that is reasonable based on the problem we're working. So what we're going to do now is I'm going to plug some things in. But to do that, I also want the value of Na plus, since that's a constant too. So I'm going to solve it first, and then I'm going to plug some stuff in. So Na plus, and you can do this in a bunch of different orders, but this is the order I'm going to use. We added 20.1 milliliters, so 0.02010 liters. It was 0.1 molar. And our volume of our solution is 0.03010 liters. From there, this will be 0.06678 molar. So that's the concentration of my sodium plus. That's a constant. So now I'm going to plug that in, as well as both concentration values for HA minus and A2 minus into my equation. Let's see. Yeah, that's all I'm going to plug in for now. So now I'm just going to plug in some constant numbers I know. So this gives me 0.6611 plus 3.322 times 10 to the negative fourth equals H2A plus 0.06678 plus H3O plus minus A2 minus. I combined like terms. I have minus 2 plus 1. Like combine those, you should get minus A2 minus. Now I'm going to move all of the constant stuff together. And so what I get when I combine all three of those is negative 3.378 times 10 to the negative fourth is equal to H2A plus H3O plus minus A2 minus. Okay, so what I need to do now is I need to reduce the number of variables. I still have 3 variables in this equation. H2A and A2 minus are both concentrations that I don't know the value for. But I do know the value for HA minus. It's going to be equal to, we solved that earlier, is 0.06611. And I'm going to make the approximation that's reasonable. It's a species that's in large concentrations. Problem, it's not going to change a whole lot. And so I'm making that approximation. So if I can get this in terms of HA minus and H3O plus, then I only have one variable, the H3O plus, which will give me my pH. Now, what I need to do is I need to take both Ka statements and I need to rearrange those. So I'm going to do that now. I'm going to move to the next slide. So if you are following along, make sure you have this equation because I'm going to be substituting into this equation on the next slide. Okay. So from there, let's get our rearrangements. So first, Ka1, if I look at what Ka1 looks like, I have that Ka1 equals HA minus times H3O plus divided by H2A. Now, if I rearrange that to solve for H2A, what I get is that H2A equals HA minus times H3O plus divided by Ka1. And as a reminder, we know Ka1, so that's a constant, and we know Ha minus for this specific problem. So now I just have my variable H0 plus. Then I also do some rearrangements of Ka2. So Ka2, if we go back to our equations, is A2 minus times H0 plus divided by HA minus. And this one, the rearrangement's going to look a bit different. I want to get A2 minus by itself. So I'm going to move everything else over. So I have Ka2 times HA minus, sorry, the minus disappeared in my bracket, divided by H0 plus is equal to A2 minus as a species. So now I have an equation for A2 minus and H2A. So I'm going to plug those back into the equation on the other slide. I'm going to go back for a second in case you need to look at it. So that's this equation here. I am plugging in for these two values. That's where I'm putting this into now. And then the H0 plus will stay. So from that, when I plug those in, I get that negative 3.378 times 10 to the negative fourth equals HA times H0 plus over Ka1 plus H0 plus minus Ka2 times HA minus, it keeps making it disappear, divided by H0 plus. Now, I want to solve this equation, and one of my problems is my variable is H0 plus. Remember, HA minus is not a variable in this case. I'm missing the minus over there. So I want to get H0 plus out of the denominator here. It'll make it easier to solve. It'll set this up as a quadratic. So I'm going to multiply everything in this equation by H0 plus and get H0 plus squared instead. So this will give me negative 3.778 times 10 to the negative fourth times H0 plus is equal to, I'll combine like terms in a second. So HA minus times H0 plus squared. Note that if you want to, you can change H0 plus to X if it makes your life better. It's slightly less to write. So if you do that, as long as you write down as a note you did that, that works pretty well. Here we also have H0 plus squared. And then for the last term, the H0 plus cancels out with one of the denominators, so we just have Ka2 times HA minus. Now, I'm going to rearrange this. So one thing is I am writing a lot of these algebra steps. You can, if you're really comfortable with your algebra, there are definitely times where you can combine two of these steps at the same time. So I'm going to real quick erase the stuff above here. That way I can leave this thing on the bottom so you can reference it as we do the rest, because I know it's hard to follow as I go between them. So give me just a second. This is not the fastest eraser in the world. Oh, actually, just a second. I will pause this and erase it, then come back with it there. And there, through the magic of editing or remembering my recording software has options, it's all erased. So now I'm going to do some stuff. I'm going to combine like terms, and then I'm going to plug in constants where they have, and then I'm going to solve them using the quadratic equation. So when I combine all these, I want to get 0. I'm going to get 0 on the left side because to be able to use my quadratic equation, I need everything equal to 0. And then I'm going to move this H0 plus term over to the right, and I'm going to combine my two H0 plus terms to make it into one variable. So when I combine the two terms, I will get HA minus divided by Ka1 plus 1 times H0 plus squared. So that's just taking my two H0 plus squared terms here. And remember, for this one here, because there's nothing in front, it's like there's a 1 in front. So I just factored H0 plus out, and then I'm left with the other terms. Then I moved my H0 plus over. When I did that, I changed the sign from negative to plus because I had to add it to both sides. Plus 3.778 times 10 to the negative fourth times H0 plus. And from there, I then have minus K2 times HA minus. Now for this one, in the interest of time, because this video is already long enough, you should plug in the values for Ka1 and Ka2, as were shown earlier in the video. This value here for HA minus, we're going to treat as, make sure I've got that right, 0.06611. And if you do that, I'll also note this, let's see, this term over here, when you do that, you're going to get 60.027, because that one, in case you got the math weird. And so you'll get that. Plug in Ka2 as well. You get a value at the end. I'll just go ahead and put that in. It won't take that much longer. So this term over here is going to become 2.5849 times 10 to the negative 7th. Note, I'm just keeping extra things so I don't have rounding issues. So now A is 60.027, B is 3.778 times 10 to the negative 4th, and C is negative 2.5849 times 10 to the negative 7th. Plug those straight into the quadratic equation. When you do that, you'll get two values. Only one of them is positive, so you will get that H0 plus equals 6.287 times 10 to the negative fifth, which will give you a pH equal to 4.20. So this is how to do the longest type of titration problem there basically is. So that's how you would do that. That's how you use a mass and a charge balance to think through doing a problem like this when you can't rely on Henderson Hasslebalch, the presence of only one species in an amount that you have to pay attention to. So since we can't make either of the two approximations we often do, this is how you solve this. Thankfully, you only have to do this occasionally, and then everything else we can make some approximations that make problems way faster than this. So hopefully this helps out and makes this more clear, and I will have another recording you can reference for doing all the other types of calculations that will probably be about the same length of this, even though it's like 5 problems. So, thank you.